So good afternoon, everyone. My name is David Huard. I work at Uranus, and I'm co-convening this session with James Hebert from PKIC in Victoria. And the session is about the electronic delivery of geophysical science services. And we'll start our presentations with Simon-Philippe Breton, who you can now share your screen. So we have 12 minutes presentations followed by 3 minutes questions. Thank you.
Thanks, David, for the introduction. So today, thanks for being here. Today, I will present tools to visualize operational forecast fields from the MSC, but also products that are particular to a wind energy project that I'm working on, like Icing maps. I will then provide details about this particular project. So this work was done in collaboration with Franco Petrucci, and we are both working at the MSC, which is the Meteorological Service of Canada. More precisely, we are working at the Canadian Meteorological Center, the CMC, which is the National Center of Numerical Weather Predictions on Supercomputers, which is located in Dorval, Quebec. The main project I will be telling you about implies making icing and wind forecasts for wind energy. This project is financed by Natural Resources Canada since 2016, and its goal is to provide high-quality supercomputer numerical meteorological forecasts to the scientific community performing R&D to optimize the integration of wind energy in the electrical network. We have three main external collaborators on this project. For the Icing part, we have Nergica, which is the Renewable Energy Research Center located in Gaspé, Quebec. We have the University of New Brunswick for the wind ramps part. And we have also the Wind Energy Institute of Canada, WECAN, that provided us with observation data to apply a Kalman filter that I will tell you about a bit later. Let's start with the icing part. So icing on wind turbines can cause several problems. For example, it can lead to larger fatigue loads, to ice throw, or to decrease in production, which is the main focus of our work here.
Sorry to interrupt. You're not sharing your screen.
Sorry?
You're not sharing your screen.
I'm not sharing my screen. Oh, I'm really sorry.
It's okay.
Okay, sorry. Thanks for telling me. Okay. Okay, I was here then. It's good. Okay, you did not miss too much detail then. Sorry about that. So this icing, then it can cause modification to the blade aerodynamics, lowering the production, or it can also it can also do that you have to shut down the turbines if too much ice accumulates on the turbine, and it can imply several $1 million in losses for large wind farms. So it's important to investigate this. So our goal here is to improve forecasts of icing and of related production losses. In order to improve the icing forecast, we have developed what we call an icing suite that allows us to provide our collaborators with more detailed information than is available publicly from the operational model outputs. This suite is based on the outputs from the HRDPS, which is the high resolution deterministic prediction system that is run at the CMC 4 times a day with a lead time of 48 hours. And there are two parts from this to this suite. There's a part that extracts and interpolates data at over 20 lat-long stations corresponding to wind farms in Canada. And there's also a part that does it on a small grid located in the eastern part of Canada. And what we do is that we use this data to apply internally an icing algorithm based on the work of Yang et al., whose reference is given here. And this predicts icing accumulation on a cylinder. And then we also send our data to Nergica that also applies this icing algorithm, and they also perform energy loss calculation going from an ice accumulation to an energy loss. And they also perform some verification work. And for the grid part, we have recently begun to make data accessible on a WMS server at 3 model levels in an experimental mode. I'll show you an example now. So first of all, WMS stands for Web Map Service. It's a standard protocol for serving geo-reference map images over the internet. Data on the server can be visualized using, for example, the web interface called MeteoSound Plus, whose link is provided here. I used it in this case to visualize our experimental icing results that are made available publicly, as seen in the screen capture that shows an ice accumulation as forecast to occur in this zone here in millimeters per hour at a level of about 80 meters for the 48-hour forecast of this run in late March this year. So you can see that we have ice that is forecast in this zone. And once you know what kind of field is available from using this interface, then we can access the data using scripts written in Python, for example. Then we have much more flexibility on what we can do with the data. And I show here an example of what can be done. Sorry, I went too fast. So what I show here is net accretion rate in meters per second at a model level of about 80 meters. For a run in late March last year. It's shown here as a video that is made up by superimposing Icing map forecasts for 18 hours. And you show that you can see that you have an imported system that is forecast to produce Icing that is to travel in the zone. So you can see that we can develop quite interesting, very interesting products by accessing these data. And then more generally than what we can get from particular to our Icing projects, we wanted to show you as well what platform that can be used to interact with the operational model outputs at the CMC. This platform is called GeoMet, and I show its web page here. It can be accessed by by Googling Open Data GeoMet. And it's the official MSC platform that provides public access to the MSC data via API. So API is application programming interfaces. So the same mechanics can be used in this case to interact with the data as with the MSC server, WMS server I showed you before. But in this case, GeoMet is the official version from the CMC. SMC. So here I will show you an example of what we could do by interrogating the database using Python to get the output from an operational model at the CMC on the subgrid shown here. So what I did in this case is that I extracted temperature maps at a height of 2 meters from the HRDPS using Python for a forecast run last week in this case. So I put the temperature maps one after the other for 48 hours to make a GIF file, and this is the result that I obtained. And this could be done for various operational models at the CMC, so this is very interesting, we think. And we showed it would be interesting also to show you the script that was used to get this GIF file. It's very simple, as you can see, it's only a few lines, everything is there. And it can be done from any PC by using standard Python packages that are imported at the beginning. And if you wanted to access our experimental Icing products, for example, you will only need to change the link in this rectangle here, and you can use the same type of commands for the rest to access and make videos and so on. And important to mention is that we would like to make such scripts available to the interested users so that they can interact with our data. And then let's move to the wind part of the project where we focus on forecasting wind power ramps. So power ramps are large and sudden changes in wind energy production, either going up or down in power, and they result from changes in the wind resource. They are difficult to predict, and they are a challenge for the industry as down ramps will force network operators to use other sources of production to compensate, while up ramps will force them to offload, to wasting energy, not to overload the network. So what we want to do here is to improve the wind and power ramp forecasts. So in order to improve the power ramp forecast, we've been running GEM ourselves on a small grid shown here. So GEM is the model that is used at the CMC to perform numerical weather predictions. So we run it with the same resolution as the HRDPS, but our goal here is to increase the time resolution of the output. So we output the data every 3 minutes versus 1 hour for publicly available data. So with this, we aim at better determining the start and the end of ramp events, which is quite interesting and useful for the industry. And from these runs, we interpolate the data at wind park locations and heights, and we send it to UNB, which works on identifying and forecasting power ramps. So going from wind forecast to power forecast. And they also work on developing an interface for the industry, and they also perform some verification work. And let us mention that we are doing this in an experimental mode, but we are looking at the possibility of also running small grids at more locations in the country and outputting the results every 3 minutes, and to make these results available on the same type of platform that was that I shown you before for the Icing forecasts. Going back to the operational products from the MSC, I showed you before how to extract a temperature map from an operational model using GeoMet. Now I would like to show you how this platform can be used to extract a time series of a given variable at a specific lat-long location that I chose here as Energica's experimental site location. So in this case, I use Python to extract the wind velocity from the HRDPS at 10 meters height as a function of time of the forecast, and I plotted the result to obtain this figure. So we see here the wind velocity as a function of forecast time. So it's quite easy to do. I do not show the script to do it, as it's similar to in simplicity to the one I showed you before, but it's quite easy and it makes it really powerful, we think. Going back to our own work, in order to improve the wind forecast, we are going further in our project than 2.5 kilometer runs. But we are also running in an experimental mode, GEM, using a 250 meter resolution on the small grid shown here at the northern tip of PI, where the Wind Energy Institute of Canada is located. So we do it by doing a cascade from the 2.5 kilometer run to 1 kilometer and then to 250 meters. I show here an example that illustrates the kind of difference in the detail of information we can get by comparing on the left the 2.5 kilometer resolution output with the 250 meter one on the right. So what we see here is the wind velocity at a height of about 45 meters as forecast for this run in late May last year. So we see that we get more detail in the figure on the right with a higher resolution. So we believe that the representation of the topography and land-sea interaction for this site is better, but we still have some more verifications to do to quantify the improvement that we get. Then we are looking at even more ways to improve our wind forecast. So we have been working on applying a Kalman filter to improve the forecast at the same site, for which we have had access to observation data from 2019 and 2020 that was measured on the mast here. So you see how complex this site is with the land-sea interaction. You have some ice here, you have some sharp edges to the island, and you see that within even 1 kilometer here, you have a lot that changes. So this site is quite challenging and it's interesting to study it further. Now more information about the Kalman filter itself. So it's a collaboration with WCAN that allowed us to obtain observation data at their site. The Kalman filter code was written by a colleague. It uses past observation data for training, and it's applied in post-process to improve our 2.5 kilometer resolution wind forecast with 3-minute outputs. And we are willing to also redo these experiments with 250 meter resolution outputs. So we tested this filter from day 82 to 195 of this 125-day period shown here, using the 81st days for training. And to quantify the effects from the Kalman filter, we square the errors between the observation and corrected or non-corrected forecast as a function of forecast time, and we average over the number of days where the Kalman filter was applied. So the blue curve in this case is for the non-corrected forecast, while the red curve is for the corrected one. So we see that even with a 2.5 kilometer resolution forecast, which is rather low for that kind of site, which is quite challenging, we get from applying this Kalman filter notable improvement for the first 3 hours of the forecast, which is quite important in the wind energy industry. And we are curious to see what kind of results we would get by using a resolution 10 times higher as input data to the filter. Now, I think my time is up. I just want to conclude. So I've been discussing ways in this presentation to access MSC data, both operational and experimental, using standardized tools. The experimental data are related to wind energy project that I've been describing, and they are available. Some of them are available on the WMS server, and more products specific to wind energy, like 3-minute wind outputs, will also be made available. And I've also shown you the official platform called GeoMet that can be used to access operational model outputs from the SMC. And these data can be visualized or extracted using scripts, and scripts will be made available, as I said before, for users who are interested. And on that, I would like to thank you for your attention, and I'll be happy to answer any question you might have. Thank you.
Thank you, Simon, for the very clear presentation. I'd like now to invite questions from the audience. Just please raise your hand or unmute yourself. And while people think about questions, I have one. So is the data extraction, so you showed an example with WMS to show images, but to get the actual numerical data, are you using web coverage service or another API to do so?
That's a good question. I've been investigating this. I think it's web coverage, WCS. I've seen that. I'm not an expert on this. I think it is, but I'm not sure. I'd have to check that.
And do you think it will scale to products at 250 meters resolution? In the sense that, is it a standard appropriate for high resolution data?
That's a good question too. I've not thought about this. I'll need to investigate that. Thanks for the question.
Oh, good, no problem. And since there doesn't seem to be any more question, thank you again, Simon, for the presentation. And we'll move now to Travis Logan from
Thank you very
Uranus.
much.
Thank you.
Okay, thank you, David. Does everyone see my screen?
All good.
No. So my presentation is called PAVX GIS, Integrating Online Climate Services with Geographic Information Systems. So I work at the Uranus Consortium, so I'm a colleague of David's. And we worked for this particular work, we worked with an external consultant, Camilo Perez Erro, who is an external GIS expert for helping guide us through some of this work. So I'd like to thank him as well for his help on this. So before diving into anything else, I thought I'd do a quick summary of what the PAVX platform is. So PAVX is an online platform for the analysis and visualization of climate data. So the platform is hosted and maintained by Uranus, and it's developed in partnership and collaboration with various other organizations. So some of their logos are at the bottom, both in terms of collaboration and in some cases financial support. So what it is more concretely is somewhat of a difficult question because the platform can be different things to different users. So in one sense, it is a hosted Python environment via a Jupyter Hub, providing a Python analysis environment, as well as access to some key climatic data sets via a dedicated thread server. In another case, components of the PAVX platform have been deployed as more of a back-end solution jointly with more traditional websites. So climatedata.ca is a case where this has been used. So Carrie and Elaine will be presenting that website following my presentation. So that's a good thing. So in this case, PAVX web processing service have been deployed alongside the website, and in order to enable custom calculations of climate indices on some key data sets through a fairly user-friendly interface. And in a very simple case, PAVX could be seen as simply as a remote data service where I could access data sets through various protocols, OpenDAP or web coverage services, some of these OGC things that we've just heard a little bit about in the previous presentation as well. So that's sort of the overall view of how it works. And moving on, basically the sort of overall focus for us providing user access up to this point has been this Jupyter Hub environment. So the hosted Python environment with libraries for analyzing climate data, some Jupyter Notebook tutorial material to walk people through navigating the data sets, analyzing the data sets, and examples going from simple visualizations to some intermediate visualizations as well. So that's been sort of our main focus. And so for this work moving forward, the sort of question is, why are we interested in GIS users? So there's a number of reasons. Basically, our thinking is that GIS users are sort of present almost in everywhere when you go out there. So multiple disciplines, both in the private and public sector. So a few examples of various sectors here in the slide. In terms of public government, it's multiple levels as well. So it could be at the municipal level up to the federal level, depending on the ministries. There's GIS experts typically in all of those various levels. And these professionals are typically data savvy and with at least some sort of programming knowledge or experience. And so that's the idea, is looking at ways to get climate data and services into the hands of professionals that aren't necessarily climate scientists. So this other way of providing a user experience on PAVX with the Jupyter Hub has been relatively well received via government researchers and academia, but they're typically people who are fairly familiar with manipulating climate data sets themselves, and we wanted to sort of focus on maybe avenues for providing these data sets to people who are sort of outside of that sort of user group. So there's lots of experience there. There's lots of disciplines, and there's more and more overlap in terms of the technologies that are provided. So PAVX is built on tools of Conda environments, so Python environments in using Conda, Jupyter notebooks, as well as these sort of data protocols provided by the OGC or other international standards, which are more and more supported directly within the GIS. So it seemed like an interesting exploration that we could take a look at moving forward, with the overall idea of thinking that these are the folks who are going to be eventually using the data in terms of making climate change adaptation plans and things like that. So for the rest of the presentation, the idea is to sort of present some of our initial explorations in terms of providing data access, visualization, and I'll touch a little bit on data analysis directly within the Esri ArcGIS Pro environment. So as much as possible, we'll try to look at the scenario where we're using these sort of internal ArcGIS Pro Python environments. So they're just a clean install. We haven't tried to add too many dependencies. In certain cases, normally when things didn't go too well, we did look at the opportunity of cloning the ArcGIS Conda environment and adding a few PAVX dependencies to see if we get a little bit further along. And the overall examples will be looking at accessing climatedata.ca datasets, so the maps and figures that are on the website. There are copies of the same data files on the PAVX thread server, so that's all accessible. And the sort of reasoning behind that has been mainly that the site has been fairly well received. It's been online for a number of years now. And really, maybe one of the drawbacks that you could see from this sort of traditional websites is that you can visualize the data, but there's no way of say overlaying any private or sensitive information on those maps and figures. Whereas if we can pull the data from the remote PAVX server, bring it into the ArcGIS environment and have that map in front of you, and then you could add your own sort of information and overlay that into your own maps and figures and things like that. So that's kind of the reasoning behind the exploration. So moving on in terms of data access and visualization. So we'll start out with the sort of simplest scenario possible. So the first sort of data protocol that we'll cover is this web coverage service. So this is the Open Geospatial Consortium protocol for pulling raster data remotely. So the sort of simplest possibility is simply using some of these graphical tools built into ArcGIS to make a remote connection to a WCS server. I won't get into too many details, but basically the story here is that we didn't have too much luck with something as simple as this, trying to connect to the PAVX service. Basically, we got as far as having a successful connection. So I was able to create a remote WCS entity here in this client. I have a number of data variables that are connected to this coverage, but I wasn't able to actually display any of the data within the map. There is some trouble with some metadata in terms of truncating of variable names and things like that, and there seemed to be no real indication. We knew on our side that this is multidimensional data set, so there's a time dimension here, but it didn't seem to be any real indication in here. So that wasn't too successful. We weren't too surprised by that, but we thought we would start with the simplest scenario possible. Moving on in this case, so we moved on to the scenario where we've used a cloned Conda environment, so the Python environment that comes with ArcGIS, and we've added a couple of PAVX dependencies to allow us to follow steps that are outlined in some of the online documentation. So accessing web coverage services, sorry. So, and in this case, the actual example online in the documentation is accessing GeoMet that we just heard about, but basically following some of the same steps, modifying some of the inputs that are different between what PAVX is providing versus GeoMet. I was able to get a little bit further. So we were able to connect to the service. We were able to clearly visualize some of the data layers within them. In terms of accessing the various time steps, there's a way to basically to do a simple for loop over the time positions that are provided within the coverage service. And basically what we've done here is for each time slice, we've created a geotiff file and saved it locally, and then we can display it within the GIS fairly simply. The main drawback that we were finding with the web coverage services, at least those provided by the thread server on PAVX, was that there seems to be a lot of loss of the metadata, which is fairly key. So basically, accessing the data, I would have sort of fairly opaque variable names indicating variable IDs and ensemble percentiles and the various emission scenarios based on this climate change projections, but that could be fairly difficult to figure out what I'm actually looking at in this case. So the metadata seem to get lost in translation in this particular case. So that seemed to be somewhat successful, but we thought we'd try one of these other data protocols that is supported by PAVX and seem to be supported as well in ArcGIS. So going back to this sort of simple case of graphical tools to access some of these data layers, there's tools, basically it's called make a multi-dimensional raster layer. And in this case, the only thing that we've really done differently from a traditional approach here is instead of providing a local path towards a data set is that we've provided the OpenDAP URL. In this sort of input category, I've been able to connect to the remote data set, successfully visualize it in the map frame of ArcGIS Pro. It comes as described with a multi-dimensional support. So the ability to select all or some of the various time steps and then enable time sliders and do either jump between time steps or do an animation. It's actually possible as well to make multivariate GIS layers, which I didn't really know was possible, but basically you can group some of these various data layers that are available in the service into a single layer, and then there's mechanisms for changing in between those directly within the GIS as well. In terms of metadata, we got quite a bit better, but maybe not perfect. So within this interface, I have, again, my same sort of variable codes that are hard to know what it is, but I also have some indication of the number of time steps that are in each one of those data sets, and a much more descriptive description from one of the metadata fields within the sort of netcdf files that are on the remote server. So quite a bit better, but it is sort of missing one key one, which would be sort of the units attribute that would be normally found in the netcdf file seems to be missing. So it depends on how this description is written. Sometimes you can figure out what the unit should be, but it's not explicitly shown. So that was one of the things that was not perfect. And then in terms of the real difficulty we found here was that this kind of remote access to these data layers could end up making ArcGIS Pro pretty unstable. So the minute we got beyond 2 or 3 or 4 of these remote data layers within the map frame, ArcGIS Pro would typically crash fairly regularly. So investigating load on the thread server itself, so the tools that we have to monitor things on our end at Uranus didn't seem to indicate anything drastic. So it seems to be something, probably the hypothesis is that it's on the client side, on the ArcGIS Esri side, that things get unstable with these sort of remote layers. So, but all in all, that was much more successful than maybe what we had with the web coverage service protocol. So sticking with the same data access OpenDAP access protocol. If I had a recommendation of how to move forward, this would be sort of the pipeline of data processing that seems to be the most promising right now. So within the internal Conda environment of Python, one of the dependencies is the library Xarray. And Xarray just happens to be one of the key or core libraries within the PAVX tools as well. So that was kind of interesting. So something that we were familiar with on our end on the climate side that we could maybe use to help us along. So the overall flow would be to access this OpenDAP URL using Xarray, and then that permits us to have access to all the key sort of metadata attributes that you would normally find in a netcdf file. We then used Xarray to save the data to a local netcdf and sometimes to subset it as well. So that's really to help us with the stability problems that we were having. And then this multi-dimensional raster layer creation is also available via the internal ArcPy library. So we can combine that in a fairly straightforward Jupyter notebook to create these multi-dimensional raster layers that can integrate layer names incorporating units of long name, description, or whatever combination we want to provide. So we have something that is descriptive to the user and stability coming from the fact that we've saved that netcdf file locally. Again, there is some limit here. Displaying these layers in the GIS, ArcGIS seems to use a lot of CPU and RAM, so there's some limitation there in terms of the number of layers that you can get into the thing, but we had much more success using this sort of pipeline. So that would be a sort of recommendation, at least as of now, in terms of trying to get some of this data into the ArcGIS environment. In terms of data analysis, I'll speed up a little bit here. Like I said, our main focus was just looking at data access and visualization, but in terms of analysis, the sort of blending of things that we have been focusing on PAVX, so basically the Jupyter notebook avenue has been our main focus, with some of these internal tools kind of makes a pretty interesting overall package that seems to have some potential. So once you have these multi-dimensional raster tools, there are some interesting things that you can do just internally that have been developed within the GIS environment. So point layers or polygon layers of extracting points and making graphs, either multiple variables for the same point or multiple locations for a single variable. So you can make some of these graphs. On the flip side, having Jupyter Notebook support let me pretty much run some of the tutorial analyses from the PAVX homepage. So if things are missing, you can sort of use the Xarray library to access data as you would, say, in the PAVX Jupyter lab, and do some things that may be limiting. So the overall package seems to be fairly promising. I guess there's some care that would be needed in terms of, say, adding dependencies to fully run PAVX examples. You have to add a few dependencies, and I did manage to break the overall Conda environment a couple of times before I managed to run things properly. And then in terms of running, say, basically the big difference here is that if I'm running a PAVX Jupyter Notebook example, in my ArcGIS environment, the big difference here is that the analysis is being done on the local machine. It's no longer being done on the PAVX server. So all of the data is being streamed over the web, and the data processing is happening on your laptop or on your PC or things like that. So there could be some limitations in terms of processing power or bandwidth issues if you start doing large extractions of larger regions. So in my example, I've been pulling up point locations, and it seems to work quite well. But there is also, I don't have time to really get into the idea of PAVX web processing services, but there is the possibility to use a different avenue where requests are made to the PAVX server, the crunching is happening server side, and the result is what you would be receiving on the end here. But I didn't really have time to get into that sort of example, but there could be some workarounds there in terms of processing power and things like that. So just in conclusion, I think the overall conclusions that we have is that this PAVX GI integration is, although it's not seamless out of the box, but it seems to have a fair amount of potential, and that sort of blend of what we've already been doing on the PAVX Jupyter side with what is available on ArcGIS seems worth exploring further. So what we're working on now, what we hope to get together is some guidance documenting what we've basically the explorations that I've described so far, but in a much more understandable manner. And then the plan is to have a public GitHub repository with some well-documented examples and sort of recommendations for GIS professionals hoping to access PAVX data. So I'd be more than happy to answer any questions if there aren't.
Thank you, Travis. I'll ask people in the audience to ask questions on the chat, and so you'll be able to respond there. As well, we'll try to keep on time, and I'll invite Elaine and Carrie Pomeroy to present the last presentation.
Thanks, David. Elaine's just going to pull up the slides here.
Hopefully that's working.
I hear
Great.
you fine. Please go ahead.
It's great on my end. Thanks, Elaine. So hi, my name is Carrington Pomeroy, and I'm a physical scientist at ECCC's Canadian Centre for Climate Services. I work in the Data and Products Office with Elaine, and I'm going to let her introduce herself here.
I'm Elaine Barrow. I'm a senior advisor with the Data and Products Office at CCCS.
Great. So can you just switch the slide here, Elaine? Okay. So today we're going to be talking to you about our climate data portal called climatedata.ca that was developed about 3 years ago in the interest of providing actionable climate information. So climate information in a format that's usable to folks looking to incorporate it into their decisions or their planning. And we've been working on this site, updating it regularly, continuously ever since. So we're going to be quickly discussing the idea and main goals of the project before going into its defining features, components, and then we'll talk a bit about what we've learned and what we're going to look to do going forward. And one of the main things I want to point out right off the bat is that this project was undertaken as a partnership. And so ECCC has been collaborating with the country's leading climate service providers in URANOS, the Pacific Climate Impacts Consortium, and the Prairie Climate Center. And we've been working with an information technology company, the Centre Recherche et Informatique de Montréal, CRIM, and a front-end developer, Habitat 7. And we think so far this has been one of the biggest parts of climatedata.ca's success, as we've been able to work together well to provide this data in the best means for our users. And next slide, Elaine.
Yeah, should be.
And that's, yeah, perfect. And so providing this data together goes a long way towards accomplishing our goal of lowering the barrier to incorporating climate data into decisions. Historically, climate data has been seen as complex and inconvenient for those looking to use it, and they're not wrong. The most common climate data format is a NetCDF, can't be used by any sort of Microsoft products. The data is often all provided in one file, which means that the user has to try and slice and dice a multiple gigabyte, multi-dimensional file on their own. And this isn't even getting into complexities associated with having to deal with multiple models, multiple mission scenarios, and other things like that. So what we're trying to do with climatedata.ca is to take a couple steps out of that equation give users the means and the guidance, and guidance is underlined here, to identify the information they're interested in and put it into practice. So in essence, we're trying to use climatedata.ca to make accessing climate data feel more like a convenience store than an inconvenience store. And so Elaine's going to point out how we do that next.
Okay, so just in case you aren't familiar with climatedata.ca, I had a quick look at the participants, and I think most people are, but just in case you're new to climatedata.ca, I'm just going to quickly go through some of the main features of the portal, and many of which you do see on other climate data portals, and then I'll hand back to Carey for him to talk more about the computing side of things. So while we provide access to both climate projections and observed data on climatedata.ca, the functionalities that we've developed to date have focused on the visualization and analysis of the projections, although we are intending to expand those functionalities to the observed data sets in the future. So the climate projections that we provide are from the Pacific Climate Impacts Consortium. So this is their downscaled and bias-adjusted CMIP5 ensemble, which has got 24 models within it. And it's at a spatial scale which is more appropriate to decision making. So it's about a 6 by 10 kilometer resolution. The projections are available for 3 emissions pathways, the RCPs, and they span the range from low to high emissions. So all of the variables and indices that are available have been derived from maximum and minimum temperature and precipitation. But we do have one other CMIP5 data set, and this is the relative sea level change data set, and that has been prepared by Natural Resources Canada. And we'll be updating the whole site shortly to add in the latest set of climate projections from CMIP6. So if you click on any of the variables in this list, it takes you through to the map interface to visualize the data. And this interactive page allows you to choose or change the variable index. It allows you to select the time frequency, so monthly, seasonal, or annual. And it allows you to select the emissions scenario or change emissions scenario and compare 2 emissions scenarios side by side. And then on mouse over, you can see the median values and the range value for each grid box highlighted. And then you simply click on any one of the grid boxes, and this takes you through to the time series charts. So these charts are summarizing the projection information for the location that you've selected. And they're also interactive in that you can turn on or off the RCPs here. You can add in some modeled information, and you can also select to view 30-year averages or 30-year changes with respect to 1971 to 2000. You can also download the information or the images from this point, or you can go through to the download page using the top menu bar here to select multiple grid boxes and things like that to download the information, both at all of the monthly, seasonal, annual, and the daily time scale of the original data set. Okay. So what makes it different from other climate data portals? Well, we've worked with different sectors. So we've worked quite closely with some of the different sectors. So we've got transportation, agriculture, health, and buildings. And from this engagement with users in those sectors, we've identified features which those sectors consider important. So both health and agriculture requested that we package the data differently. So we've aggregated the data by watershed, by health region, and by census subdivision. And in a very similar manner to the grid interface, you simply click on one of these regions and it will take you through to the time series information for that region. And then we had a request for a functionality to be able to calculate heat waves using different temperature thresholds, which came from the health sector. And this led to the development of the analysis page. And so the Analyze tool on climatedata.ca is really what sets it apart from other climate data portals. And this functionality allows the users to analyze the climate model ensemble using threshold values which are most relevant to their situation. The process returns the ensemble statistics, which can then be used to construct time series charts very similar to the ones which are available for the pre-canned variables and indices. So this analysis can be done at the grid box scale or for one of the regional options that we provide. And the users can select from a wide variety of indices that are based on temperature and precipitation in this menu on the left, and simply by selecting one of the options and then filling in the relevant threshold value. So the analysis can be for single or multiple grid boxes. It can also be for a subset of models known as the PKIC 12, or for the full ensemble of 24 models. The user can request the analysis be for 1, 2, or all of the RCPs we have available. And they can also ask for different percentile values rather than the 10th, 50th, and 90th default values that we provide. The user then simply submits the request, and then we'll receive an email with a link through to the data once the processing is complete. This usually takes about 10 or 15 minutes, but it depends on server traffic at the time. And then finally, to support using climate data in decision-making, we come back to guidance. And this is why we've developed the learning zone. This is where users can find background information on the data sets we provide, climate science information, and guidance on best practices for using climate information in decision-making. So in essence, we provide everything to get started on the decision-making journey. And I'll now hand back to Carey, who'll talk about the behind-the-scenes architecture that makes all of this work.
Thanks, Elaine. So yeah, to enable all that, what are we looking at? In high level terms, which is mainly where I think about this, it's relatively simple. The front end was created using WordPress with a theme that was created by Habitat 7 to give it that nice aesthetic. And then we use some open source components like Leaflet for mapping, high charts for creating those time series charts. And similar to most platforms like this, climatedata.ca uses a GeoServer mapping service to access the raster information. Unfortunately, there's no magic secret to getting around the really large base data size, but we do use a couple of different tools to make the experience a little better and lower that barrier. First of all, we don't actually store any of the archived station data. So alongside all our climate raster projection stuff, we have archived station data for those looking to put some of the information into context. And this is all accessed via ECCC's GeoMet OGC Web Feature Services API, which is similar to what was talked about in an earlier talk today. As for the gridded data, the website uses an API of its own to access the data that is stored in an OpenDAP accessible thread server. This data is currently housed as netCDFs, which we'll talk about a little in a bit. And some of the data has been subset further in the interest of quicker mapping and quicker displaying of some values. And then for the analysis page, as Travis mentioned in his talk, we leverage the PAVX platform. And we use an execution management service called Weaver to execute the web processing service calls on PAVX using Finch, which is an open source web processing service specific to climate indicators that was developed as part of the Data Analytics for Canadian Climate Services initiative. So instead of storing every possible combination of time frequency and temperature threshold, these processing services are called to do the calculations for the user, hopefully on a much smaller subset than all of Canada, so they can then be accessed as smaller bite-sized files. Next slide. Thanks, Elaine. And so what have we learned throughout this process? Well, for one thing, the partnership has been invaluable. Having subject matter experts for every component of this project, whether it be architecture, climate science, training, or what have you, the teamwork has been imperative. And in some senses, I think throughout this project, we've been a bit of a victim of our own success. We delivered this platform very quickly, and it has all sorts of features. But now we've been hearing about all the other sorts of features we should add, or the things we missed the first time, or people have been asking for us to integrate their own information into the package. And now that we're trying to address these requests, we're realizing that this framework that we set up really quickly could have been better set up to accommodate the rapid growth. but we didn't know how fast we were going to grow. And so we're learning that now. And similarly, user testing and guidance have been really key. Just because things are intuitive to us, especially having looked at them for months and tested them ourselves, it doesn't mean it's going to be making sense to everybody else. And so co-producing features with users and providing guidance alongside has resulted in much more user-ready products that we've seen come out of the sector-based work that we've done that Elaine mentioned. And so given all that, the way we're looking forward is to ensure all portions of our site are open source and accessible to all of our partners or whoever else would like to develop it within reason, of course. This will result in even more collaboration, having all our partners have access to whatever part of the stack they need to work on. And it'll be more ways to share information across the partnership and with our users. Similarly, work is currently being undertaken to see if to ensure the site is better prepared to incorporate more features and data sets. For example, one thing we're currently looking at is how we could drop in Python-based applications that are a bit more climate data ready. So this way we keep all the nice aesthetic of climatedata.ca, but we have that flexibility that comes with a platform that is a bit more suited to climate data. As mentioned before, we'd like to incorporate more engagement into our development and embed more guidance into our products to help with the user readiness of them. And then the last key point is that we're interested in other forms of more efficiently storing our climate data. An example of this could be .zar files so that we can more efficiently grab the data and display it for the users, maybe more efficiently do some analysis on it and make it ready for them as well. And so that's everything from us, and we're happy to take some questions.
Thank you for the nice presentation. Are there questions from the audience? Otherwise, while people may be typing, I was curious to know what response do you get from other federal ministries? Is there interest from others in the model you've built to present data?
I can take this one, Elaine. Yes, as many of you will know, at the federal government, we're fairly limited in terms of what we can do with a federally hosted website. And so we've had quite a bit of interest. Elaine and I have participated in a couple meetings with other departments on how this process works, like how the funding is provided and how the partnership works and what the governance is like. And while not every department is capable of putting something like this together, there's certainly quite a bit of interest to follow this model in the future.
And do you think this could help you grow, like using the momentum from other ministries and their own budget to help support the effort from ECCC?
Yes, I certainly think so. I think that alongside just the momentum and the positive feedback that we've gotten on the website itself has really helped kind of push this project forward. We have another contract with CLAM at the moment to do kind of a phase 2 of climatedata.ca. And with all of this alongside the upcoming national adaptation strategy, we're hoping to even further this relationship in the future.
Excellent. Are there other questions from the audience for Elaine and Carrington or for the other panelists? If none, I'd like to thank all the presenters and my co-convener, James, for organizing this session, and wish you a nice evening.